Electromagnetic induction. We know from the Ørsted's experiment that a current produces a magnetic field. Now the question arises, is the reverse also true? Can a magnet produce current? Michael Faraday began to work on this problem in 1825. For 6 years, he experimented with magnets and coils of wire. The experimental arrangement used by Faraday consisted of a few turns of wire and a sensitive galvanometer. One day he moved a magnet near a copper coil connected to the terminals of a galvanometer coil and observed that a momentary current was produced in the coil. Faraday observed, when the magnet is stationary, there is no deflection in the galvanometer. When the north pole of the magnet is brought towards the coil, a current flows in the coil and the galvanometer shows deflection towards the light. If the motion of the magnet is stopped, the galvanometer shows no deflection. The current in coil flows as long as the magnet is moving. If the north pole of the magnet is moved away from the coil, the current flows in a direction opposite to the previous case and the galvanometer shows deflection towards the left. If instead of the north pole, south pole of the magnet is either brought towards the coil or moved away from the coil, the direction of the induced current changes. When the magnet and the coil are at rest with respect to each other, the total number of magnetic field lines, called magnetic flux, remains constant, so galvanometer shows no deflection. Whenever there is relative motion between the coil and the magnet flux linked with the coil changes and galvanometer shows deflection. The current produced in the coil by changing magnetic flux linked with it is called the induced current, and the corresponding potential difference is called the induced potential difference or electromotive force. Whenever a conductor is moved inside a magnetic field, the flux linked with it changes and induced currents are set up in it. The phenomenon of producing electric current in a conductor by moving it in a magnetic field is called electromagnetic induction. Let's do an activity in which the moving magnet is replaced by a current-carrying coil and the current in the coil is varied. In this figure, the magnet is replaced by coil 1. When current is made to flow in the coil 1, the primary coil, the needle of the galvanometer instantly jumps to one side and just as quickly returns to 0, indicating the momentary current in coil 2, secondary coil. A potential difference is induced in the coil 2 whenever the electric current through the coil 1 changes. The induced current is found to be the highest when the direction of motion of the coil is at right angles to the magnetic field. The direction of induced current can be found using Fleming's right-hand rule, also known as the dynamo rule. It states, stretch the thumb, the index finger and the middle finger of the right hand so that they are mutually perpendicular to each other. If the index finger points in the direction of magnetic field and the thumb points towards the direction of motion of conductor, then the middle finger shows the direction of induced current in the conductor. It is very interesting to note that the electric generator, which is used for generating electricity, works on the principle of electromagnetic induction.